We are Team 11, and this is our interim presentation for the analysis and redesign of the floor tile cutter. The primary use case for our product is tile cutting. Looking at historical data and market demand, the estimated annual production volume is 3 million units. This product is targeting homeowners or contractors who need to cut ceramic tile for a kitchen, bathroom, or other space. The secondary use case for this product is glass cutting. The production volume is less than an estimated 2 million units annually. This product is geared towards glass cutting for small windows, which typically have a larger footprint than tile at a reduced thickness. While similar in their properties, glass carries a greater crack propagation. Next is a fully assembled image of our floor tile cutter CAD model. Here's an exploded view of our CAD model with a full parts breakdown. There are 13 components in total.
Now that we have discussed the chosen product's use cases and design, we will move on to product analysis. The core function of the tile cutter is to cut tile. There are 3 key functional requirements. It must score the tile. While doing so, it must control the score and transmit force. It must break the tile, doing so providing upward and downward force. It must also hold the tile. To enable this requirement, the cutter must position and support the tile. As this tool will be used to make many cuts, it must enable maintenance to assure dependability. To make the tool more convenient, it must measure the tile and enable tool mobility to move from job site to job site. Finally, the tool must reduce user fatigue.
Assembly sequence analysis, fishbone diagram. Sequence 1 is for the normal tile cutter, and for that process we start off with the base, some of the base components. We put on the rails and the front bracket, then we put on some of the cutter components, the handle, and we finish it off with the rear bracket, and finally the cutter. Sequence 2 is for both the tile cutter and the glass cutter, and to make it more efficient we delay differentiation and we start off with the handle, the cutter components that are common, and then we move to the differentiated cutter rails, base supports, and we finish it off with the front and the rear bracket. Moving on to the sequence comparison table. Sequence 1 and 2 are equivalent except for the last 2 criteria, ease of testing subassemblies and ease of assembling in parallel. Sequence 2 performs better than Sequence 1 because of the fact that it delays differentiation and allows you to take advantage of common subassemblies, assembling them earlier in the process, which allows you to test them better and assemble both products in parallel. And this results in it having 3 points higher in its total score.
Here's our functional component mapping matrix. As shown, most of the components support the primary functions of scoring the tile, breaking the tile by providing upward and downward forces, and supporting the tile during these operations. Some components also support secondary functions such as enabling maintenance, measuring tiles, and other functions. Those are generally seen on the right-hand side of the matrix.
This is our overall bill of materials for our cutter assembly. It consists of 13 unique components and 14 fasteners. Our main components are purchased, sheet bending components, die cast components, and machine components. The overall estimated cost is $48.50, with our competitors ranging from $55 to $100 US, so we're at about 20% margin with our lowest cost competitor, but we see some opportunity to improve our margins through optimizing through the DfM DFA. This is our quad chart for our assembly. Our low functionality, low cost parts is our base support, and our high cost, low functionality is our fasteners and rail spacers, which we'll be considering elimination for these 3 parts. Our high functionality, high cost are the front and rear brackets, base, cutter rails, cutter bracket, and rail bracket, which will be included as a part of our DfM DFA for improvement.
Next, we will discuss the product family design.
On the left, we have the functional differentiation table. As you can see, many functions are common for both use cases. However, for tile cutting only, it must support heavy material and prevent chipping, which tiles are prone to do. On the other hand, for glass cutting, it must score with precision and prevent cracking, which glass is prone to do. Also for glass, it has to support a larger material because glass windows are usually larger than tiles. That brings us to our component commonality table, where all components except for the base, cutter rail, and base support are common. The base and base support contribute to force transmission and tile support. These functions are critical to customer material choice, which means they have to be modules. The cutter rail is directly correlated to the cutter score in the functional component mapping matrix. The base and cutter rail are the most expensive components, but despite the high cost, their placement as modules is non-negotiable due to the functional requirements across customer variants. The base support is 8th on the BOM in cost and carries a lower impact allowing for benefits in areas such as bulk discounts and inventory management.
The first module change for the secondary customer is to the base and base support. The base and base support increase in size to handle larger glass panes and can be seen in blue. The second module change is to the cutter rail. Length is increased to control scoring over the longer distances required for larger glass panes and is highlighted with red arrows. The common interface for both of these changes is the front and rear cutter mounting brackets, which are shown in purple.
The common interfaces between the designs are found in the front and rear brackets. The rails seat into the holes identified in blue. The base of the brackets is secured to the base assembly using bolts.
Looking at the current product family assembly diagram, the part variation appears at the beginning with no strategy to prioritize common components. In the diagram for the modified assembly, we enable delayed differentiation to take place by front-loading the common components for an improved result.